So I'm sharing this lecture on YouTube. I don't know if you are able to see it. It will be nice if somebody can confirm whether it is visible on YouTube. I can check on my computer, but I'm not sure if that is the same that other people can also see.
Yes, sir, it's visible on YouTube.
Lecture on YouTube. I don't know if you are able to see it. It would be nice if somebody can confirm whether it is visible on YouTube. I can check on my computer, but I'm not sure if that is the same that other people can also see.
Yes, sir, it's visible on YouTube.
Okay, fine. So let me continue with the lecture. I see some background noise coming. I don't know how to turn it off. So let me continue with the lecture.
Sir, you probably have to pause the YouTube link or something on your computer.
Pause what?
The background noise, I think, is from the YouTube live
Yes,
stream.
background noise coming.
Sir, you probably have to pause the YouTube link
Pause YouTube.
on your computer.
Pause what?
The background noise, I think, is from the YouTube live stream.
Okay. I suppose it should be okay now.
Yes, sir, your audio has improved.
Okay, let me start. I don't want to waste any more time. Today I'm going to discuss some questions, some problems. You will see. Okay. So, yeah. Suppose that, so this is example. Suppose that A1, A2, AN are events. So events means members of script F. Okay. Events are sets, subsets of omega, for which you can talk about probability. Okay. Such that probability of each one of these Aj is equal to 1 for every j. Show that probability of intersection of Aj is also equal to 1. And here j goes from 1 to infinity. Okay. So, okay, so here it goes. So the thing is, we know that, yeah, so first let's look at just to get the hang of it. So probability of just two of them, A1 intersection A2. You have a formula for writing this. This is very much like as for union, but so this is probability of A1, probability of A2 minus the probability of A1 intersection A1 union A2. So you take this to this side and this to this side, and you see the formula looks more familiar. And this is equal to, so 1 plus 1 minus 1. So that's equal to 1. Okay. So now you can do 3 of them. probability of A1 intersection A2 intersection A3. Well, actually, you can repeat this same thing argument with A1 intersection A2 thought of as just one single set, and you have already proved this. So this is equal to, I'll take that point of view. So this is probability of A1 intersection A2 plus probability of A3 minus probability of A1 intersection A2 union A3. So it's understood exactly what is meant here. Okay. And just now we saw this is 1, so 1 plus 1. And so anyway, this is probability of A3 itself is 1, and you have added a little more, it's not going to change the probability, so it's again equal to 1. Union is no problem. I already used that here, by the way. So this is again equal to 1, and so on. Okay. If you want, you can write a general formula for A1 intersection A2, blah, 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 intersection AN in terms of all these multiple intersections of various collections. But let's not worry. You can do it more elementarily like this. And now, so you can say either by induction or something like that, by induction or otherwise, whichever way you like to do it, probability of the following holds. Probability of A1 intersection AN is equal to 1. So this is true for all n. And now you see, so we have a nested family. A1 contains A1 intersection A2, contains A1 intersection A2 intersection A3, sorry, and so on. And probability of, I mean, so intersection of all these things, AK or AJ, J equals 1 to n, 1 to infinity. This is equal to limit, well, you can say J goes to infinity, probability of A1 intersection up to AJ. This is equal to 1. The constant sequence 1, therefore the limit is also equal to 1. And that's exactly what you wanted to prove. Okay, so we are done. So here is another problem. These problems are from the book. So suppose you are given that, suppose that you are told at least one of the events A1, A2, some bunch of events AN is certain to occur, and that no more than three of these events AN can occur simultaneously, Okay, no more than, no more than 2. Let me erase that. No more than no more than two of these events can occur together. Okay. Uh, suppose that it's a long problem, but easy to solve. Suppose that probability of each one of these is equal to P, and intersection of any two of them, AR intersection AS, is equal to Q, if R not equal to S. Okay. Then show that some inequality P is bigger than or equal to 1 by n, and Q is less than or equal to 2 by n. Okay. So let us do that. Uh, so okay. So what are we told? You are told that at least one of the events is certain to occur. So if I take the union, therefore, so given uh, the the hypothesis, this implies, I had to implies that probability of at least one of them occurring is certain. So that means that if you take the union, that's equal to 1. And no more than 2 can occur. Okay. So probability of AI intersection AJ intersection AK, this is equal to 0 if I less than J less than K. Of course, they are arbitrary otherwise between 1 and n. Okay, so you are told this, and now you can write. So now you compute this P of A1 union AN. This is equal to summation probability of AJ and minus summation probability of two of them occurring, AI intersection AJ. So this is I is strictly less than J. Sorry about that scribbling. Hate scribbling. Okay, I is strictly less than J. So here each one of them is P. So this is J going from 1 to n. And here 1 less than or equal to I less than J. So this is equal to P by n. N times P and some negative quantity. Okay, and you can in fact write what that negative quantity is. So this is this is n. So there are n choose 2 times probability of each one of these is same. So that's why you can write n choose 2 times q. Okay. So well, this is now this is given to you. So given, so this is equal to 1. Therefore, well, you are taking away some non-negative quantity, and NP minus that is actually equal to 1. And that means that NP must be bigger than or equal to 1, or P is bigger than or equal to 1 by N. Okay. Uh, yeah, so now can Q be very small? Okay. Q cannot be very small because this quantity uh, has to be um, so NP must be so we know that, yeah, NP yeah so Let us write this. So this must be uh, so the question is whether Q can be very large. So if it exceeds 2 by n, let us see what happens. Okay. So suppose that Q is bigger than 2 by n. Okay. Then, so I have n times n minus 1 by 2 Q. This must be bigger than n times n minus 1 by 2 and then 2 by n. Okay, so this and this cancels, this and this cancels, I get this is bigger than n minus 1. Okay, now np minus something n, so now np, so p is less than 1 anyway, p is at most 1. Okay, so that is what you will see. Now np minus this number, so I am subtracting smaller quantity, right? So this is bigger. I'm going to subtract smaller quantity, which is, so I write here and choose 2 anyway. So 1 is equal to, we just have to look at this. This is all that you need to do. What is this? This is and choose 2q. And I'm removing something smaller. So this becomes bigger. np minus n minus 1. Okay, so p is maximum equal to 1. So I'm going to put the maximum value n minus 1, which is equal to 1. But you see, that is what you get is 1
So I
is to
think it's
3
the
bigger
other
than
way
1.
around, sir.
1
So I
is to
think
3
it's not greater than, so it's less than.
is 1.
So
I'm
P is
subtracting a smaller quantity. Therefore, this quantity is, oh, okay, sorry. Is less. Okay, sorry. Yeah, thanks. This is, yeah. And here also. I am putting something maximum for p, which is 1. So then this becomes bigger. So n minus 1, which is 1. So I get that n. Yes, thanks. This is less than 1. It's a contradiction. A contradiction. Therefore, q must be less than or equal to 2 by n. Very clear, right? Yeah. Okay.
Sir?
Yes.
So could you scroll up to the question now?
Can you see that?
Yes. So it says P of AR is equal to, like probability of AR is equal to P, right? For
For
some,
every p.
I did.
For every r.
Oh, for every. Okay.
And here also
Yes, sir.
for every r and s are not equal to s.
Yes, sir. Yeah.
Okay. So
Yes,
all
yes.
these events occur with equal probabilities, and that common value I am calling it p. And then intersection of two of them, any two of them also occurs with the same probability q, independently of r and s. And then you have to get this inequality. So yeah, so this is, and you are told that so intersection of three of them, if you take, the probability of that occurring is 0. So because no more than two of these events can occur together. Okay, so that's the interpretation for that, and that's why you can just stop with this. Otherwise, you will have some more terms. Yes. Okay, and now this is the case, and so you just use this inequality. It's rather very easy to see p is bigger than or equal to 1. This is also easy to see once you suppose that If Q is too big, then you are subtracting something too much. And so you should get this number to be less than 1. Okay? Because the maximum possible value for P is 1. So this already you have N, and this quantity therefore should be at most N minus 1. So that's exactly, yeah, what we got. And yeah, so that gives the answer. Okay?
Yes,
All
sir.
right. Yeah, so now I want to, there's not much time, so unfortunately I have to rush through, and I will not be able to discuss all the solutions for all the problems. I mean, the solutions to the next problem in full detail, but as much as I can, I will do that. So this problem is motivated by considerations in statistical physics, it seems. And for us, it has been formulated in a purely mathematical fashion. So suppose that it takes a long time to write the question, but nevertheless, I must. Suppose that there are n particles. So you can think of them as either n balls or n letters to be delivered to some number of mailboxes and so on and so forth. Sorry, what did I write? I keep thinking of probabilities and particles and n, let's say, cells which the particles can occupy, can occupy. Okay. So n will just generally assume that bigger than or equal to small n. And more than one particle can occupy the same cell, and and the particles are identical, but they are distinguishable. The You can think of them as labeled particles if you like. The particles are uh, you can say labeled, and otherwise identical. Otherwise identical. Okay. Uh, so, uh, so each particle can occupy. This is given to you. Each particle can occupy any cell with probability probability 1 by n. Okay. Now there are two questions. Find the, so let me call this A. Find the probability that uh, uh, the particles each the n particles occupy n cells, n given cells. Okay. So you have to look at the wordings rather carefully. N given cells, one in each cell. And the next one, so the thing here is, and I draw your attention to this, given cells, n given cells. Okay. Now the next one is, there'll be exactly one, there'll be exactly one cell, one particle in any cell, in any cell. Okay, and here that means that so there will be n cells that the particles occupy, but that's not pre-assigned. Okay, so let us do this problem. Yeah. So okay, so answer to A. So see, there are these. Let us put these boxes, pictures of these boxes like these. And there are n of them. Okay, n boxes. So any particle can occupy any of these n cells. There are capital N many cells. So number of possible configurations will be so number of possible occupancy pattern is equal to n power n. Okay, the first particle can be here in any of these things, and then the next particle can again, there will be capital N many choices. So total number of choices will be n power n. Okay, out of this, so you are told that so we can always assume that without laws of generality, the particles must occupy only these cells. Okay, and one in each. So the first particle can go into any one of these n. So the number of possible cells the first particle can occupy. First particle can occupy equal to n. So for the next one, because two particles are not allowed to be in the same cell, so it has to be in the remaining n minus 1 cells. So on. The choices for the number of choices for the jth particle is n minus j plus 1. So in all, the number of choices or patterns equals for the particles to occupy the given n cells is n factorial. So it's like, you just have particles labeled 1, 2, 3 up to n, and then any arrangement of those particles will give rise to a possible occupancy pattern. Okay, so there are exactly n factorial. So therefore, in this case, the required probability is equal to n factorial divided by n power n. Okay, yeah. Now for the second problem, for B, well, I mean, if you fix the number of choices for n cells out of capital N cells, okay, equals n choose n. And so you view this second condition as follows. So no restriction on which collection of n cells they should occupy, but exactly one particle occupies each cell. that means that your choices, you pretend like this. So you first choose a sub collection of n cells and then arrange them according to the first scheme. Okay, so therefore the number of ways of ways of arranging n particles in n cells, no, not more than two in each cell, not more than one in each cell, is you just choose that n cell first of all and then do the first problem and choose n times n factorial by n power n. Okay, which you can slightly simplify. Well, I will not do that. Should I do that? N factorial by n factorial, n minus n factorial. Here n factorial by n power n. So this can be cancelled and you can simplify that. Okay. Now there is a variation on this theme. So you see how if we change the condition slightly, the answer changes drastically. So now, so this is, let us give this some name or label 3. Okay, this is 1. So in condition 3(2), same as 1, but the particles are not labeled and not distinguishable. So they are completely identical. So you cannot tell apart. Okay. So then the problem changes. So it's like suppose. For example, if you have something like this. So previously, so if the particles were labeled and you had like this, now this must be viewed as 2, 1. Okay. So this is the situation. In this case, how do we proceed? So I need to get more space. Okay. So you understood the distinction between these two. So yeah, so this is to be written in bracket. So not part of the problem, just for you to understand. Okay. So how do we do this? The thing is, here is one way to do this. So you first of all think of these n boxes arranged like this, capital N many boxes, and then you write these particles indistinguishable, not labeled, anything. Okay, like this. So these are n many particles and these are n boxes. Arrange them in just a single line. And what you do is you just fix the first box, and permute the remaining ones in any fashion you like. Okay, so here I'm going to draw the same thing, but then these stars are. So I just want to say, permute them any which way you like. Permute these objects, box objects. No distinction is being made between boxes and particles. Then you will get some pattern. And when you get this pattern, you just put the particles into the box which is to the left of them. So you see, you may get after you perform something like this, some pattern like this may happen. And in between, there may be some particle like this, and then one particle, and maybe some box is there, but is to the left. Okay, something like this. But if you get something like this, then you view this as, well, this particle goes into this box. Okay, so it is occupied. The next one is not occupied. This one is occupied by two particles. And then this one by one particle. You understood, no? So this is the way I view them. So in other words, this occupancy gives me a permutation of this, and conversely also, any given sort of occupancy pattern, I can sort of move the particle to the right and get a pattern like this, okay, which will correspond to exactly a permutation of this. So therefore, the total number of occupancy patterns. That's a Y occupancy pattern. Total number of occupancy patterns is equal to. So there were totally capital N plus small n, but this one is always fixed. So this one is fixed, so that I can just always push to the left. Equals n plus n minus 1 factorial. That many arrangements are possible, right? So factorial. Out of this, see now, okay, total number. But see, I'm going to divide by something here. I have to say why it is so. N factorials and then n minus 1 factorial. N minus 1 factorial. Okay, so the thing is, if you just permute these particles among themselves, that has no effect. Yeah, because the particles are indistinguishable. So you see, I could have changed this particle, exchange this with this one, and this with this one, and so on. Then the resulting occupancy pattern will be exactly the same. I see the particles are indistinguishable. They are not labeled. You cannot tell them apart. So only thing that matters is the number of particles in each box. Okay, that being the case, there is an over count. How many, in view of this fact that the particles are not the same, distinguishable. So that is why there is this thing. What about these boxes? You may sort of think that these boxes are labeled 1, 2, 3, and so on. Okay, either way, whichever way you like to think of them. And then I sort of moved these, permuted them, but that again doesn't really matter. Occupancy pattern remains the same if the box, for example, is they are permuted among themselves, but then n minus 1 boxes are there, so I just factor out that n minus 1 factorial, because that many factorization will not change any pattern. The patterns are told to you, and if you change just the boxes, permute the boxes among themselves, Okay, we always keep this one fixed so that we can always move the particle to the left. This doesn't enter into the picture at all, only the remaining n minus 1. And so these divide by n minus 1 factorial to get total number of occupancy patterns. Okay. So what is the answer? This is just the total number. The answer for the first one, see, that means that you are saying only one out of, yeah. So so these, like I said last time, so you fix these small, yeah, these first n cells, okay, first n cells, little n cells, and then you find out how many ways in which you can put this um, uh, one particle in each one of these. There's exactly one way because the particles are indistinguishable. So the if we fix the n cells for n particles to occupy no more than one in each. So let me write that, one in each. That's a condition given to us, right? One in each. One in each cell. How many ways are there? There's exactly one way. There is exactly one occupancy pattern. Sorry for the terrible handwriting. So therefore, probability of that happening, therefore the required probability in this case is 1 by total number. So 1 by n plus n minus 1 factorial. In the numerator, I have n factorial divided by n minus 1 factorial. Okay. And for the second thing, now, yeah.
So shouldn't the n minus 1 factorial also be in the numerator?
See, that is to be expected because the total number should add up to what? N plus n minus 1. Yeah. So I'm just saying total number of occupancy pattern is see,
So the
if you
capital N
distribute
minus
the
1
particles
factorial.
among themselves,
So no, sir, it should be in the numerator in the final answer.
No, I have, no, here you mean I am computing the probability, no?
Yes,
This
so you
is the
divide
total
one by
number. 1 by, there is only one way in which you can get the favorable event to happen. So 1 by, sorry, this one, sorry. This is what you were saying. Absolutely, yeah. No, scalars. Yeah. Absolutely, you are right. Okay. All right. Okay. For the next one, if the n cells are not fixed, then the required probability is this is for A and this is B. Probability equals exactly as before, n choose n, and then divided by the total number of possibilities. So n plus n minus 1 factorial, n factorial, n minus 1 factorial. Okay. That's it. So, and there is one other way in which you can pose this problem, and that is, Uh, so now change the problem slightly. You are told that two particles cannot occupy the same cells. Okay, and now do 1 and 2. Otherwise, the conditions are the same. Particles and the particles are indistinguishable. So let me also say that. And the particles are indistinguishable. Then the total occupancy pattern. I sometimes scribble. I have not much control over the pen. Total occupancy pattern. Total number of occupancy patterns is equal to, well, I mean, this case is really very simple because you see, you have capital N many boxes. You just choose some little n boxes out of it, and the particles can go into those boxes, okay, in exactly one way because the particles are all indistinguishable. So this is n choose n. And if you say which n boxes in which, so solution to n, solution to A probability is equal to one. There's only exactly one way, so n choose n. This is, I suppose, correct. That's it. Yeah. So that solves the problem. Now it's all okay. I still have some nearly half an hour. Next thing is I want to talk about this famous problem called the Bertrand's paradox. There's a reason why I want to discuss this. Okay. So let me tell you what the problem is. The problem is the following. So you draw a circle. On a blackboard, I can draw a good circle, but here on this device, it's a bit difficult for me to draw the circle. Okay.
Sir?
Yes?
So sorry, could you just scroll up for 1 second, sir? I just missed something.
Yeah. You see,
okay,
previously, this was not told to you. Previously, it is quite possible that more than one particle can occupy the same cell. In physics, you have this, sorry, I have not studied physics beyond school. So, but nevertheless, Pauli's exclusion principle comes into picture here, and that tells you two particles cannot occupy the same state. Okay, so if you are told that is, so you see, first of all, probability theory is a way of reasoning out based on given knowledge. As your knowledge improves, your you know ignorance decreases, and therefore you can make a better estimate, or you can um, make a better guess, or find the correct way to say is find the probability. You have to rework your probability in the light of new knowledge. Previously, you were not told that it is physically impossible for two particles to occupy the same cell. You were not told that. So you had to allow for that to happen. Now you know that two particles cannot occupy the same cell. Okay. And once you know that, your answer becomes different. See? Okay. This, I
Yes, sir.
hope, yeah. Does it answer your question? Maybe that's what I didn't
Yes,
let you
sir.
know. Can I
Yes,
go
sir.
on?
Yeah.
Yeah. So these are, there are some names associated to this. I feel very diffident to even pronounce those names because, as I say, I mean, I confess I don't know any physics. Okay. But once the problem is formulated in mathematical terms, you just do your mathematics. So the first thing, these are important problems. I should said that. It's just that. Okay, so the first thing is what is called Boltzmann statistic. Okay, and the next one that we worked out is called Bose-Einstein statistics, and the last one is Fermi-Dirac. Okay, so these are three different sort of um, uh, concepts which arise in statistical physics. So the assumptions we make are coming from consideration in physics, okay, about nature of particles. But we formulated it purely mathematically and then solved the problem. Okay, so that's what I have done. All right. Uh, Now, what is Bertrand's paradox? It's a very interesting. Really, this sort of gives some insight into um, why we need to have a very rigorous formulation of probability space. Like I had mentioned, you should know your omega, you should have your script f and the function p. Okay, here is a problem. So you take a circle and you draw a card at random, maybe one card like this. And now you measure the length. And it's perfectly meaningful question to ask, what is the probability that the length of this card is more than the length of the side of an equilateral triangle that can be inscribed on this circle. So once this circle is given to you, length of the equilateral, the length of the side of the equilateral triangle that can be inscribed on this circle is determined. Okay. Now I draw a card. Maybe I draw a very small card, and this is another. One is already drawn. This is another, and this is another. And maybe a third one. I mean, just you keep drawing cards like this. Now I ask, what is the probability that a randomly chosen card will have length more than the length of, or at least the length of the side of an equilateral triangle inscribed in this circle. Okay. Now you need to have a way of, um, making a mathematical model out of this. So you need to come to an understanding about how, okay, how you will count or um, uh, measure this or formulate in terms of um, you know uh, mathematical in mathematical terms which will capture this problem. And one way is the following. So we are going to give three different ways. Okay, and in each of these three ways we will compute the probabilities. Okay, and you will see what happens. So first way, in view of the symmetry, view of the symmetry in the problem, symmetry in the problem. So I didn't say what the problem is. Okay. So this is why it takes a long time to write down. I should have probably. So here is this thing. So I will a chord is drawn, is chosen at random. Chord in a circle is chosen at random. Find the probability. Its length is bigger than or equal to length of the inscribed, not the inscribed. Okay, length of the side of now inscribed equilateral triangle. Sorry about that. Okay. In view of the symmetry in the problem, we may fix and in view of yeah, okay, so I'll say this following thing in the fact that any parallel family of chords is perpendicular to the diameter we may parameterize the chords by points on the diameter. Points on a diameter. So in other words, what we are saying is you just look at a family of parallel chords. Okay. So I draw a picture once again. Now draw a diameter and I only look at chords which are parallel to this. Perpendicular to the diameter. So parallel family of chords. Okay. I can always look at that. It's enough to look at it because of the symmetry in the problem. Okay. So now this is my point, one endpoint A, another B, my now. So just draw chords like this. This is how I parameterize parallel families. It's enough to look at parallel families because of the symmetry and so on. Okay. Now, question is, so each one of these, of course, they meet the diameter at exactly one point because I look at those which are perpendicular to the diameter. Okay. So points on the diagonal, points on a diameter AB. This is the first thing. Now, from geometry, very simple geometry, I'll come to that. So from geometry, so take a point X here and then draw this CX dx or just CD. From geometry, the length of the chord, length of CX, so CD, okay, just parameterized by XCX dx is bigger than or equal to length of the side of equilateral triangle, side of an equilateral triangle, equilateral triangle in the circle, inscribed in a circle, if and only if, okay. So I'm going to dissect x lies in the interval, Okay, so in which interval? I'm going to write here A1, B1. So this is some interval in AB. So, okay. It would have been easier if I had taken the unit circle and done it, where, so yeah, the AA1. So I'll just draw the picture here. I think it's much easier to say it and saves time. So this is the center. And now A1 and B1 are midpoints of these radii. A1, B1 are midpoints of AO and OB, where O is a circle. O is the center. Okay. So what you are saying is, so you take, in other words, you take this diameter AB, and if so, you just choose x at random, and if x happens to be between these two, A1 and A2, okay, A1 and B1, then, well, the length of the chord would be more than the length of this side of the equilateral triangle inscribed on the circle. So it's natural to stipulate that probability that x will lie in this interval is length of A1, B1 divided by length of AB. Or in other words, if you choose any interval here, what is the probability that a point chosen at random will fall in this interval? That will be, so if this is J, then length of J divided by length of AB. Okay, probability that x is in J is equal to this. Therefore, the required probability is equal to so 1 by 2. Okay. Why is it that this is A1 and B1 are midpoints, and why does it become relevant? That's a simple elementary school geometry, maybe 10th, 8th standard. So I leave that to you to verify that. Okay. Some picture. So you draw the equilateral triangle. My diagram is pretty bad. So this is a diameter AB, and with B as a vertex of your equilateral triangle, draw this. Okay. And see where it hits. Here is where. Similarly, you can draw another equilateral triangle with A as a vertex, and then draw this diagram and see where is this point. This is my point B1 and this is a point A1. And you can see that the center is actually the center of gravity of, center is the centroid of the equilateral triangle, and that will tell me, and that this median divides the, this center therefore divides a median in the ratio 2:1. If you put that together, you get the answer. You get this this fact that this is from here to here, this divides it into 3 equal parts, and this is 1/2 of it. Likewise, this is another half of it. Okay, so that gives us the probability equal to 1/2. Now there are 2 other models. So second way, solution number 2. And here what we do is, how do we view this? This is maybe much simpler model. Again, because of the circular symmetry, by symmetry, fix one vertex. Okay, so here it is A. All right, and here is my O. It's not so relevant anymore. And then what you do is, you just choose any other point on this other than A. Just choose any other point and call it maybe B here, and draw this. Okay, and when is the chord going to be larger than that L, length of the thing? So you draw that equilateral triangle. Okay, so I'm going to draw the equilateral triangle in just a minute. Let me draw the equilateral triangle so here I'm just going to erase this. Okay, the equilateral triangle with A as a vertex, okay, will cut this into 3 equal parts, 3 equal chords. So here, and A itself. So this one is my equilateral triangle. Okay, it doesn't look quite equilateral, but anyway. So probability of success. So the favorable event, so let me write in blue, the set of points which lead to favorable point. So set of favorable event is equal to the arc. So here, let's just call this P and Q. Length of is equal to the arcs equal to AB, AP, arc AP union arc AQ, where APQ form an equilateral triangle. Equilateral triangle. Okay, so that means that, but then you see all the 3 arcs, they have the same length, right? AB, length of the whole circle is now divided into 3 equal parts, and the favorable parts is 2/3. Sorry, favorable part is not this. We want the length to be more. The length is more if, for example, this AB has length less. Okay, what I wrote here was wrong. If you want longer thing, then you should go for this. Okay, this part. You see, this chord is longer compared to this one. For example, the diameter is the longest one. Okay, so I wrote something that is not quite right. It should be PQ. What we want is something more, yeah. So PQ. Okay, and so therefore the required probability is
So
the required probability is equal to arc PQ, length of the arc PQ divided by the total circumference of the circle perimeter. This is equal to exactly 1 by 3. And previously we got, I think, 1 by 2. There is now one more method, and I'll do this very quickly because it's really very easy to say. So parameterize the chord by its midpoint. Okay. So if you take a chord, you just take any chord, it is parameterized by its midpoint. Once I know the midpoint, well, I just join it to the center, and that gives me a line, a radius, and you draw a line perpendicular to that. So that is how I parameterize it. So you see, this is perpendicular. Of course, this line comes for free once I pick this point. Of course, you may say, what will happen if I choose my origin itself to be the same? If it is origin, just draw. I mean, you can either omit that, or it's a diameter. In any case, you know the diameter has length more than the side of an equilateral triangle. So, okay, parameter is by its midpoint. Now, the favorable event is when the midpoint lies in the circle with same center, O, with same center and radius equal to 1/2 the original circle. And this means what? And this means that probability. So you see, now what you have is probability, how to compute probability. So you see, you have a big circle and you have another small circle. So if the point X, the midpoint of the thing, lies within this smaller circle, then the chord will be longer. Why that half comes exactly as for the case in the first thing, same type of reasoning. I leave it to you. It's a very simple elementary geometry. And so this means that this chord will have sync. Okay. So this shaded region. And it's reasonable to expect that probability of the favorable event is the area of the region in which X falls compared to divided by the area of the whole circle. So therefore, the required probability is equal to area of smaller circle divided by area of the big circle. Which is equal to 1 by 4. How much is this? 1 by 4. Because radii are in the ratio, sorry, I wrote 1 by 2, but it should be 1 by 4. Radii are in the ratio 1:1/2. Therefore, this is it. Okay, so you got 3 different answers. Why is it that there are 3 different answers? Does that mean mathematics is inconsistent and so on? So here, each time your omega is different, the problem may be the same. The model you used each time gave you different probability function. So depending on your model, your answer is going to be different. Which is the true model? Which is the correct model? Well, that is because you were so where exactly is the problem? If there is a well-defined problem, there has to be a unique answer. At least there should be some resolution to this problem. The thing is, you are never told in this one, a chord is chosen at random. What does it mean to choose a chord at random? And each time we gave a different interpretation for this. And depending on your interpretation of that, sort of ill formulated or imprecisely told problem, your answer was different. Think I'll stop here for today.
Sir,
Yes.
Is there like any some interpretation that will always give some rational answer?
Not necessarily. It will depend on the problem.
Like in this problem,
maybe
can we
you can
find
find
a
a
way?
different interpretation, and that will give you something else. But yeah, it doesn't have to be necessarily a rational number. I mean, in this problem, we obtained each time.
I mean, will it span the rationals? Will there always be some way of assigning the probability function, way of choosing randomness, so that it will span the whole rational numbers? Here we.
What do you mean by it will span the rational? I mean, are you talking in general terms or about this particular problem?
In this particular problem, if we can we define randomness in different ways, so that the probability will come some rational number. There, for every rational number, there will be some choosing of randomness. I
don't know about that. I only know 3 formulations. These are, I mean, none of them is due to me. I mean, this is what is called Bertrand's paradox. And so 3 different ways of interpreting the problems were given, and each time it just so turns out the answer is a rational number. In general, there is no reason to think that you will have to end up in some rational number always. So we will see a lot of situation where in fact, I planned on doing one more problem, and that I will do next time. This is there you will see that pi comes in very naturally. And in fact, this experiment, the problem I will talk about in my next lecture, that problem was used to obtain estimates for pi. Okay. So, yeah, there's no reason to think that you should have some only rational number as an interpretation. Depending on whatever interpretation you have. So even, I mean, okay, for Bertrand's paradox, only these 3 interpretations were given. Maybe there is some other way of doing things in a different way, but I only know these 3. Okay.
So what did you say was the problem? That randomness is not well defined in the question.
What does it mean to choose a chord at random? So in the first way of interpretation, I said that, well, it is like choosing an X on a diameter. You fix a diameter, you choose an X, and that's my random choice. Okay. So that was what I convinced you because of symmetry and so on. First of all, it's enough to consider a family of parallel chords and so on. And so once you have that family is parameterized by points on the line, and there also, well, we make the assumption that probability of X falling in an interval is the proportion of the length of the interval to the diameter. So these are the assumptions we made. Okay. And in the next one, we thought of a family of chord as those given by having a fixed vertex A, and then allowing the vertex B to vary. If you vary B, you get different answers. So this is another parameterization. So this is, what does it mean to choose a random chord? I say, well, choose a chord, choose a point on the circle. Okay, so this is a different formulation. So my space omega is completely changed. My omega is points on the circle. In the previous first thing, my omega was points on a fixed diameter. And the third one, my omega was the whole circle, the interior region of the circle. Okay.
So in your third one.
Pardon?
In your third method, there's infinite number of diameters which aren't counted. Like
it
which
doesn't
are
matter. You see, okay, that corresponds to only one point, and point has no area. So it really doesn't matter. I mean, it is taken care of. You will see that.
So points have no area.
Yeah, so we see we are defining probability in terms of proportion of area. So, okay, so this requires a little more explanation. So if you have a region as your possible sort of sample space, and then you want probability that your favorable event is a smaller region, E, then what is probability of E? This is just area of E divided by area of the whole region. Now in this formulation, it's okay if I omit a point. It's okay to omit a bunch of points, finite number of points. Okay, so that type of thing, and it really doesn't matter. You just omit a point, the area doesn't change.
So what that also that's not what I was saying. So I was saying that for any other point, if we omit one point, then that omits only one chord. But for this point, it omits an infinite number of chords.
But it doesn't really matter. It's just because of circular symmetry. Yeah. So, okay, you can say that, well, therefore it ignores a whole lot of things. Yes, that is something you can say that.
So that's why it shouldn't be bijective.
Okay, I admit it. It is quite possible that, therefore, you can say just for the point alone, you need to have a different probability assigned, perhaps. Yes, that is, in fact, that's a valid criticism. I completely agree. Yeah.
Sir, I have one more interpretation where the answer we get.
But you see, just once again, but you see, when you say chord and so on and so forth, okay, we took care of all the chords except diameter, but you see, again, because of the symmetry, there is only one diameter, because any other diameter is sort of equivalent to this. Of course, there is multiplicity. You see, all other chords are uniquely determined by a point, but only diameter is not. So, okay, these are valid criticisms. Yes, I agree.
So I have a very simple interpretation where the answer we get is 1/3. Can I say it's a very small one?
Sure.
So we consider the angle subtended at the center by the chord.
Yes.
So if it has to be larger than the side of the equilateral triangle, then the angle subtended should be greater than 120, less than 180. So that gives a range of 60 degree. And the sample space we have is 0 to 180 degree. So 60 degree by 180 degree, we get 1/3.
So what is the answer finally?
1/3.
1/3.
Yes.
More or less, it amounts to the same thing. Okay, so we'll stop here for today, because I know you have lecture also to attend, and my time is up. So I stop sharing and see you in the